Today we're going to be talking about Freefall. Before we get into Freefall, we're going to take a look at this experiment. So, we have two identical balls that both start off 10 meters above the ground. The ball on the right is in Freefall, which means only the force of gravity is acting on it, and it's basically just in air, so it's falling without any other forces except gravity. And then on the ball on the left, this ball is actually rolling horizontally off the table at, let's say, 2 meters per second. So, which one do you think is gonna land on the ground first? If you said both of them land at the same time, because you remembered what we said last time, you're right. And remember, we're talking about the moment this ball leaves the table, that's when this ball is dropped. So when they're both dropped, they both land at the same time because they have the same acceleration. Now, even if this object was bigger than the other one, but they start at the same height, they both take the same amount of time to reach the ground. Okay. So now, let's look at another example. So now, what is freefall? Freefall is when an object is only acted on by gravity. So this ball is just in the air and no forces except gravity are acting on it. So first, let's make a free body diagram. So a free body diagram basically shows what forces are acting on the object. So we'll make this little oval or circle the object, and we use arrows or vectors to represent forces. So we know that the force of gravity is always acting downward. So we're gonna make an arrow going downward. And then we're gonna label that F sub G, because force due to gravity. Okay, so now that we know that there are no forces acting upward, because there's no normal force, because it's not on a surface, and there's no horizontal force because it's not moving horizontally or accelerating horizontally, we know that the only force is the force of gravity. So now if we're giving the mass of the ball, which let's say it's 3 kilograms, we can find out how much force is acting on the ball. So to do this, we can use Newton's second law in the rewritten form. So F sub G equals mass times acceleration due to gravity. So F sub G equals 3 times 9.8, and F sub G equals 26.4 newtons. So an easy way to remember the unit for force is who made the law, who made this equation, and we know that's Newton. So the unit for force is newtons. And what is a newton? Newton is kilograms. Newtons equals kilograms times meters over second squared. That's the basic definition of it, and this becomes newtons. So it's like a simplified unit. Okay. Now we're going to talk about if the object is moving at constant velocity or accelerating only in the horizontal direction. So let's say this ball is moving at 2 meters per second to the right, and it's moving at a constant velocity, which doesn't really matter, and the ball just left this table. So first, actually, let's take a look at if this ball was on the table. So what forces would be acting on it? So let's make a free body diagram. This is the ball, and then we know that the force of gravity is acting downward. Oops. And then now we can see that the ball is not actually accelerating in any direction, so we need balanced forces. And we know that the ball is on the table, so we can make a line that's perpendicular to the table, and we can call that normal force, or F sub n. And because it's not accelerating in any direction, we can put this little line here to indicate that these are the same length. And if we use Newton's equation, sum of forces in the y direction equals mass times acceleration in the y direction, and the sum of forces in this case would be F sub n minus F sub g, since they're in opposite directions, and we usually use up as a positive and down as a negative, equals mass times acceleration in the y direction. And we know that these are equal, so that would be 0 equals mass times acceleration. And we obviously know the ball has a mass, so let's just give it the mass of 3 kilograms as well. So that means we know that the acceleration would be 0 meters per second squared. Okay, so after we prove that, we can look back at the free fall ball, so not when it's on the table. Okay. Now, the free body diagram, since there's no surface acting on the object and the ball is actually accelerating downward at 9.8 meters per second squared, or we can say negative 9 meters per second squared, we know that there's no normal force, so the unbalanced forces are only acting downward. And since it's a constant velocity, we know that the forces in the horizontal direction are equal, or there's no horizontal forces at all, which in this case there are none. Okay, so now we're going to be talking about kinematics. So first equation we're going to be talking about is for constant velocity. So we can see in this equation, or this example, the ball is moving at a constant velocity at 2 meters per second to the right. So the equation for this, if you remember the equation for speed equals distance over time. Probably been taught this before, and the units are meters per second, because units for distance are meters and the unit for time is going to be seconds. So since velocity is just speed, but with a positive or a negative, since it has direction, it's also going to be in meters per second. However, in physics, we're not going to say distance, we're going to be saying change in position. So delta x. And delta is the Greek letter delta, and it stands for change in, and the change in x in this case, and that over time, just like speed. And this is also going to be in meters per second, since they're the same components. Now, we're going to get on to acceleration. So, we know that acceleration is the change in velocity over time. So it has basically the same format as this, the velocity and speed equation. So it's going to be the change in velocity over time. And we know that this is meters per second, and this is seconds, which would equal meters per second squared. Now a common way to rewrite this would be acceleration equals velocity final minus velocity initial, or it could also be v naught, which is v0, over time. And the way to rewrite it, you usually write v final, velocity final, equals a acceleration times time plus velocity initial. Okay, so now that we have this equation, we derive this equation, we can go to back to the example where we know that the object is accelerating at negative 9.8 meters per second squared, and we know that the ground is going to be 10 meters as the first example right here. So we know, let's say we can put a little chart of what we know. So VF we don't know, and we want to figure that out. So that's basically the velocity of the ball right before it hits the ground. And then acceleration, we have the acceleration, which is negative 9.8 meters per second squared. Then we have time. We actually don't have time, so that's also something we need to find out. And velocity initial, we know that the ball was not accelerating at all in the vertical direction, so we know that this is 0 meters per second. Okay, so now the question is, how do we find the time? So remember this the velocity equation. Constant velocity equals the change in position over time. So we can also note the velocity in the x direction equals 2 meters per second. We already know that. And we also know, actually, let's just say that the distance that the ball is going to travel is going to be 10 meters. So from where it started to where it landed is 10 meters. This will be the delta x. So delta x equals 10 meters. So now that we know this, we can piece everything together. So let's start off with the velocity equation. Velocity x equals delta x over time. So we can rearrange this as time equals delta x over velocity in the x direction, which equals 10 over 2. And if you want to write the units, that's a good thing to do, because you can write 10 meters over 10 meters per second squared. And remember, when you divide, you can also multiply the units, either inverse or the opposite, which would be 10 meters times 1 over 2, that's 1 second over 2 meters. And now we can cancel these meters, and we're left with, and cancel this 2 and the 5, and we get, or 10, and we get 5, and we get 5 seconds. So it takes 5 seconds for the ball to get to its destination, or 10 meters away. And we also know that that point is where the ball hits the ground. So now we can put it into the acceleration formula, or the rewritten version. So VF equals VI plus A times T. So this equals 0 plus acceleration, negative 9.8 meters per second squared, and times time, which is 5 seconds. Now we can cancel this 1 second and this squared, and we are left with negative 49 meters per second. And notice how the meters per second matches with velocity and the seconds match with time. So that's why it's a good idea to write down your units. So now we know that the object reached negative 49 meters per second right before hitting the ground at the 5 second mark, or when it landed 10 meters away from the original spot. Next video we're going to talk about two more equations in kinematics and how to use them.